Hello everyone, again welcome back to our latest lecture session. So in the previous sessions we have been discussing precipitation, and mostly we have been discussing the relevant aspects about kinetics, and then we moved on to equilibrium, and that we have a new equation in this particular case as in precipitation, where we have the solubility product or the solubility constant, and then we started looking at the relevant aspects of how to solve for our equilibrium, right, as in to be able to calculate how much solid will precipitate out and so on and so forth. So obviously for that we need to develop our equilibrium model, right, and in that context we are talking about how earlier we had a phase equilibrium between the aqueous and the gaseous phase, right, and how we described x total, right, which is our component, total component balance, right, as x total in the aqueous or liquid phase and x total in the gaseous phase. So similarly now we have an aqueous phase in what do we say, equilibrium with the in equilibrium with the solid phase, right. So obviously now I am going to have x total is equal to x total the liquid phase plus x total in the solid phase, right. So it's just that we need to add a new term here, and what is that about? We need to have the relevant component that gives us an idea about the solid now, the solid that's precipitated out. So therein lies the key though. So whenever we come up with concentrations, right, so what is it that we look at? Concentration is, let's say, mass or moles, let's say, of a particular compound, let's say of x, right, per volume of that particular solution, right, which in this most of our cases is water, volume of water in which x is dissolved, right. So in general we look at mass of x per volume of the water that it's dissolved in, right. But here, you know, how do I come up with you know, expressing x total as solid, because the solid is no more in the aqueous phase, right. So it's as a solid, right. So it's the phase is different, but unlike the gaseous phase where we had partial pressure to approximate that particular activity or such, right, here we usually look at mole fractions, right, here as in the solids. So mole fraction obviously, right, if it's a pure solid, you know, number of moles of that solid per total moles will be equal to 1. So that's why the activity is going to be equal to 1. Why is that? Again, mole fraction is equal to 1, right. So how do I go about it here? So here I guess we need to tweak it a little, as in we are going to express x total, or you know, the precipitate, let's say the amount of solid that has precipitated out of the solution. So how are we going to express that as? Let's say for the solid case we are going to express it as mass of solid that has precipitated out of the unit volume of water it has precipitated from, right. So again, this is not activity or such, we are just trying to understand. Let's say I have 1 liter and 1 gram precipitated out of this particular 1 liter of water, let's say. So the concentration terms, you know, these are not strictly concentration, right. Why is that? We look at concentrations or activities in terms of mole fractions for our solid phases. Keep in mind this is a different phase, as in the numerator here is in the solid phase, denominator here is in the you know, obviously aqueous phase. Here it's a dissolved phase, right, and here it's obviously the relevant solvent here. So that makes sense here, but here the phases are different. So but what are we trying to express them as? We are, the numerator is the amount of solid that has precipitated out from the given volume of water, right. That's one aspect we are going to consider here. So obviously here how do we go about it? So here we need to first look at two aspects. One is by hand and the other is by WMINTEQ, right. So first we are going to discuss the aspects related to how to solve this by hand, let's say, right, and I guess we are going to look at a few examples later on, right, or few practical examples, and look at how to go about it. So first by hand, let's say, how do I set this up now? So this is the key here, as in first I need to identify, anyway I guess I should make the people think. So here again we are looking at precipitation, and keep in mind this is an equilibrium model, right, this is an equilibrium model, right. So before we go further, what do we need to look for now, right? Just take a few seconds to think about that, please. So here we are, so I guess what I am trying to hit at is we looked at a few conditions that need to be satisfied for equilibrium, and what's that? So first you need to know, right, if a solid can be formed or not formed, right. So here you need to make an assumption, right, and then go ahead with that assumption and see if that assumption is satisfied. Okay, let's say if I am going to assume that the solid is formed, I am going to make the relevant calculations, then calculate Q and K, let's say, and let's say obviously if I make the solid Q by K, right, and only then will it make sense, let's say. Or if the solid term comes out to be negative, what does that mean? That Q by K is less than 1. Again, let me try to explain that here. So what do I need to identify? I need to identify if the solid is formed or precipitates, right, if the solid precipitates, right. So how can I do this now? So first I can assume that one assumption, one way is assume no solid is formed, right. Assume no solid is formed, yes. So as in I am going to assume that there is no solid phase, right. So just that x total is equal to x total in the liquid phase. For example, let us say for the case of Al3 plus, right, I am assuming that no solid is formed, as in AlOH thrice solid is not formed. So I am just going to solve for it, as in Al total will be equal to what now? Al3 plus the concentration, right, plus what else now? This is just the component balance plus AlOH, right, and the charge would be 2 plus. I am just listing the complexes here, right, AlOH twice plus AlOH thrice 0 charge, this is still a complex, plus AlOH4, pardon me, negative charge, right, the concentration here. So I am going to solve for this the usual way, this is more or less just your aqueous complexes, right. So once I get the relevant concentration of Al3 plus, then I can calculate Q by K, let's say, for that particular equation, as in AlOH thrice solid in equilibrium with Al3 plus and 3OH minus, right. So once I can, from this particular case, assuming that no solid is formed, I am going to solve and calculate Al3 plus and H plus, let's say, right, and then I am going to calculate Q by K for this relevant equation, right. So what does Q by K, if it turns out to be less than 1, what does that mean? That means the solution is undersaturated, right. So thus your assumption of having no solid being precipitated out is valid, and you can say this is the final solution and I am done with it. But if you calculate that Q by K is greater than 1, what does that mean? So that means that obviously the solution is saturated, and most probably, let us say, your solid can be formed or will be formed, and thus I am then going to have to solve for a different case. So again, let us list them out here. So after solving it from the previous manner, and Q by K is less than 1, what does it mean? So undersaturated, meaning no solid is formed, right, meaning assumption is true, meaning true solution has been calculated, right. But what if after calculating the relevant variables and calculating the ratio of Q by K, and that turns out to be greater than 1, what does that mean? So it's supersaturated, right, or oversaturated, let's say, and now assumption is not valid, assumption of no precipitation is not valid, right. So thus I now have to resolve for it, and how am I going to resolve for it now? Now I am going to assume, so now I know that solid phase is present, right. So for example, now how will that Al total change now? Al total earlier was Al3 plus concentration plus all the 4 complexes usually formed, what are the AlOH, right, and 2 plus concentration plus AlOH twice plus 1 charge, AlOH OH thrice, this is still the complex, 0 charge plus Al OH 4 times and negative charge, and but now I know that the solid phase is present, so that needs to be plugged in. And what is that here? Let us say depending upon the type of solid, and assume that Al OH thrice solid is formed. So here we are going to have a new term here, right? And why is that? Because Q by K is greater than 1 from based on your assumption earlier, right? And that means your previous case is not valid anymore, right? So now you are assuming, not assuming, you know that a solid will be formed, right? And thus you have a new term for your concentration of solid. And what are the units of this particular solid now, right? Let us say, mass of the solid precipitated out, or amount of solid precipitated, amount of solid. So obviously they need to be in conjunction with the units here, as in if you are using moles, moles and so on, right? Amount of solid precipitated per the unit volume of solution it has precipitated from. Anyway, it will still be the same units, but you need to be able to understand that it's no more in the aqueous phase, right? This is a different phase. So thinking of it in terms of concentration usually doesn't make much sense. So maybe you can think of it as maybe total suspended solids, but not milligram per liter, maybe mole per liter in the, to make the units similar to what we have here, I guess, right? Anyway, amount of solid precipitated out per unit volume of solution it has precipitated from, right? That is one particular case, and you are going to go ahead and solve for that, right? So once you solve for this, you will get the relevant variables. So earlier though, you can use beta 1 star, beta 2 star, beta 3 star and beta 4 star, right, to be able to solve for or express these 4 complexes in terms of Al3 plus. All these complexes using the constants beta 1, 2, 3 star, which are more or less from your equilibrium constants for your direct and I believe protonated addition rate of your particular complex formation. So for that you can use these coefficients to express these variables as in these 4 complexes in terms of Al3 plus. But how can you express this Al OH thrice solid though? For that you are going to need an additional equation. So that is going to be an unknown, but obviously if you have an additional unknown you need an additional equation, right? So how can you get this additional equation? So you can use the additional equation as in from your solubility product, right? KSP, I guess, right? So again this will be your unknown, yes. So instead of earlier Al3 plus and H plus being your unknowns, let us say you now have an additional unknown, right? So for an additional unknown you need an additional equation. So for that you will use your equation with respect to your solubility product and then solve for your Al OH thrice solid, right, and get the relevant value. So once you get this particular value, what can I calculate further? Let us say Al total minus this Al in the total in the solid form. Well, what will that be equal to? Obviously Al total in the aqueous form. And what is that? More or less that's your, this is your Al total in the aqueous form, and obviously this is your Al total in the solid form, right? So again more or less what it is that we have been discussing here, let us say, right? So with that you can go ahead and solve for it. So again let us say if there is another method too, as in the assumption is going to be that instead of assuming that the solid is not present, you can assume that assumption is that assumption is that the solid is formed, right? And then you can go ahead with your relevant calculations, and I am going to continue with the earlier example. And let us say then I calculate this value of Al OH thrice the solid to be a positive value, right? So okay, that means a true solution has been arrived at. But if I end up with a negative value for Al OH thrice the solid, but what does a negative value mean though, right? That means no solid is formed, right? So that means assumption is not valid, right? And what does that more or less translate to? That you need to redo your calculations with no solid, right. So you can either start with either of these assumptions, as in one assumption would be assuming that there is no solid and solve for it, and then check the q by k values, and then redo the calculations if necessary when q by k greater than 1, indicating that a solid is formed. Or you can also choose or go with the assumption that a solid is going to form or precipitation occurs, and solve for the concentration of the solid that has precipitated out, right. And then if it is a positive value, that means okay, the precipitation has occurred. But if it is a negative value, what are you going to understand? I guess what do you need to understand, that there is no precipitation, and so you need to redo the calculations, removing your particular solid term and just solving for your aqueous phase species, right. So that is how you can go about it, I guess. So in WMINTEQ, how do I go about it in WMINTEQ? I believe in the initial class itself, those people who have been paying attention closely might have seen that there was an option as in specify, I believe, solid possible solid species, right. Specify, I believe, possible solid species in WMINTEQ, right. So WMINTEQ obviously cuts down on your time. So what do you need? Obviously you need to give the x total, y total and b total, let us say, right, and then specify solid species or possible solid species. So obviously if you have no clue and select everything, what is it going to look for? The true equilibrium. So it will usually look at the most stable form or the most insoluble form. But as you know, let us say if you are looking at coagulation and flocculation, your most stable form of ALOH thrice is not going to be formed. That takes way too much time. So in general, in your coagulation and flocculation, let us say, or in your where you look at sweep flocculation with respect to the aluminum, let us say, right, aluminum hydroxide complexes, it is usually the amorphous form which is the most soluble form that is going to be formed first. So you need to have that understanding about which solid is the controlling solid here, right. So specify possible solid species. So you need to look at or try to have an understanding about the controlling solid, right. And this is something we discussed in the previous classes too, yes. So I just plug this in, specify the possible solid species, right, and then go ahead with the solution, right. So I believe I have one or two examples here. First we will work it out with just the WMINTEQ and then look at how to set up the equation to also solve it by hand. So here I have alum coagulation, right. So 10 power minus 4 molar Al2SO4 thrice, and the relevant variables are given. So here obviously I have two components, they are Al3 plus and SO4 2 minus, right. So here I am going to solve it by WMINTEQ. So just means I am not going to list all the species, right. I do not need to list the species, but I need to know the total component concentrations. So the recipe is nothing but Al2SO4 whole thrice, right. That is my initial concentration or recipe species. So Al3 plus. So what is that equal to? That is going to be equal to 2 here, right, 2 times Al2SO4 thrice, that is what you see here. And why is that? Obviously if I look at the formation equation, that is 2 times Al3 plus 3 times SO4 2 minus, right, will be equal to Al2SO4 thrice, right. Anyway, this is the formation equation. I believe people should be comfortable with it without having to write it down. So 3. So obviously what does this mean here? So Al total and SO4 total. So Al total is equal to 2 times Al2SO4 thrice, not. So that is equal to 2 into 10 power minus 4 molar, right. And what is SO4 total? That is equal to 3 times the initial Al2SO4 thrice that you are adding to the solution, right. So that is going to be equal to 3 into 10 power minus 4. And with that I am ready to plug in the relevant values to WMINTEQ. So obviously again I am just reiterating what we have been doing until now. So I am just calculating the total component that I need to plug into WMINTEQ. So here obviously it is Al total and 2 into, that is equal to 2 times the initial Al2SO4 thrice that is present, right. Again, why is that? It is 2 times. So if you look at the total component, you need 2 components of Al3 plus to form your Al2SO4 thrice. So again, we have done this multiple times, and I believe I might have skipped it or have been skipping the relevant calculation, because I presume that you have now what do we say, confident enough to get this done without having to go through these write-ups, I guess, right? So let's plug them in. I need to plug in AL total, I need to plug in SO4 total. Looks like they fix the pH at 8 and alkalinity is given, and let's say I'm going to look at some particular solid, let's say. So here if it's not given, it's a safe assumption to say that ALO is thrice the solid in the amorphous form, right? Usually this is the most what do we say, soluble form which is going to be formed first. So I'm going to assume that this is the solid that's going to be formed. So let's go to WMINTEQ, I guess, right? Okay, so I'm going to fix the pH at 8. Okay, and what next? I need to add Al3 plus at 2 into 10 2e minus 4, right? 2 and e 2 into 10 power minus 4, right? Add to the list. And what else, please? And I think SO4 2 minus. Yet I believe it was 3 into 10 power minus 4, and that is something I am going to add to the list. But I believe the solution also says alkalinity is present, specify alkalinity. So it, I believe, was, what's the value here, please? 250 milligram per liter as CaCO3. So it's 250 here, 253, and I'm going to say okay, and again move back to WMINTEQ hopefully. And here, am I done with it yet? Not really, because let's say I need to specify the possible solids phases, right? So here, so limit to those species. Otherwise, if I don't use this particular option, as we talked about, we are going to have all the possible solids for all the different types of components. Well, that's an exhaustive list. So I'm going to ask WMINTEQ to limit the choice to those solids that would be present based on the relevant what is it now, components we chose. So obviously we have different kinds of solids that can be formed, but we are going to choose the solid that's going to be formed initially, which is the most soluble form, which is the amorphous form, right? So I'm going to choose that and add that, and back to main menu, right? So let's view or edit the list to be on the safer side. Okay, this is from your alkalinity addition more or less, right? And I'm going to go back to the main menu and run WMINTEQ. Okay, and so now still pH 8 is fixed. So let's first look at the species distribution. So CO3 2 minus obviously at pH 8, right? And now let's understand it holistically. So pH 8, right? Acid base relevant chemistry. So you need to know the pKa. pKa is 6.3 and 10.3. So pH 8 is greater than pKa 1. So which form will predominate now? The what is it now? HCO3 minus, right? H2CO3 would predominate when pH is less than pKa 1, right? So let's just to refresh our memories, get that down too. So here is your speciation diagram, right? And this is for HCO3 minus, and this is for, let's say, CO3 2 minus. So H2CO3, HCO3 minus, and this is for CO3 2 minus. So we know that the pKa 1 is 6.3 and the current pH is at 8. So I'm going to write this as 8. So obviously what's predominating here? The concentration of species. So obviously what's predominating? You know that HCO3 minus is going to predominate, and I believe that's what you're going to look at here. So you see that 97% is present as HCO3 minus, and that's what you would expect to based on your knowledge of the relevant acid and base chemistry. So SO4 2 minus, they are saying it's going to be present as SO4 2 minus. There is nothing surprising in that, knowing the relevant pK of H2SO4 and HSO4, right? And Al3 plus looks like you know, it's mostly going to be present as in the aqueous phase. Keep in mind this is for the aqueous phase, right? So within the aqueous phase, it's mostly going to be present as 98% as the AlOH4 negative complex, right? But here we know that we are also going to have to look at the relevant solid, right? So how do I look for that now? So here I have amount of finite solids. So the amount of finite solid that's going to precipitate out and is going to be in equilibrium is going to be 1.32 into 10 power minus 4 moles per liter. So you know that's one particular case, I guess, right? And if I look at the equilibrium mass distribution, so it tells me that if I am looking at Al3 plus, right, 1.32 into 10 power minus 4 has precipitated, and only 6.83 into 10 power minus 5 is in the dissolved phase. So what does that mean? 65% of Al3 plus has precipitated out, right? And only 35% of the Al3 plus that you put in into the solution initially is in the dissolved phase. And within this 35%, what is the form that's predominating? That was AlOH4 minus, right? So that's where we see here. So all these three correspond to only 35% of Al total, and which is present as 98% is present as AlOH4 minus. And amount of fine solids obviously 1.36 into 10 power minus 4. Mass distribution, right, 34 or 35% as dissolved and 65% as precipitated. So this is something that's obviously remarkably useful to you, right? And obviously now if you need to do this by hand, that's going to be an exhaustive process, yes. So we are going to do one particular or try to set up the equation such that we can solve one particular problem by hand, but we'll do that in the next session. I believe I have one more what do we say example here that we can look at, okay. So here I guess 2% AlOH thrice, right, and pH is 7.5. Let's also plug this in and see what it transforms into. So 2%, right, let's say per kg, let's say how much would that be present? So 1000 grams, right. So 1% would be 10 grams and 2% would be 20 grams. So 20 grams per liter, that's what 2% AlOH thrice. So here again I guess I'm getting ahead of myself. So let's say the recipe, it's a recipe problem, as in I know what it is that I am putting into the solution. So I am adding AlOH thrice or aluminum hydroxide sludge, right, which is at 2% concentration, 2%, right. So 2% per kg, it's going to more or less be 20 gram or 20 gram per liter, right. So that's what we have here, and I guess the molecular weight of AlOH thrice is going to be, okay, maybe I can use the units of grams per liter in my particular case there. So I am going to plug this in, and again I am going to assume that the amorphous form is the possible solid. I am going to specify this and Al3 plus, but because I have to, I guess, specify Al total, I need the relevant concept molecular weight. I guess it's 78 gram per mole, right, and with that I will end up with I need to calculate 20 by 78. Let me calculate that. Is equal to 20 divided by 78. Enter. So it's 0.256 moles. So the solution is nothing but it's 0.256 moles, right. So obviously Al total is going to be equal to the initial what is it now, 1 times AlOH thrice that I am plugging in, and that's equal to 0.256 molar, and H total is going to be minus 3 times, right. Why is that minus? Because it's 3 OH minus, that means it's minus 3 H. So minus 3 times AlOH thrice naught, that is equal to 0.25 times 3 is 0.75, right, and 6 would be 18, right, 0.768 molar, right, and that should be right. Anyway, minor mistake at best. So H total and Al total, I have that, and I know that the pH is 7.5, but if I am plugging this in, I guess I don't need to put in H total here, right. So I am going to plug this value and also show that it's or assume that the solid is AlOH thrice solid. So I am going to WMINTEQ, back to input menu, right, and view edit list and delete alkalinity. I need to delete alkalinity. Back to main menu, parameters, specify alkalinity and no, right. Sometimes I might need to restart WMINTEQ, otherwise it's going to mess up the relevant equation, and SO4. And what is this going to be equal to, please? This was 0.256 molar, I guess, right. So let me change that here. add to the list, and H total 2, I guess I don't need to specify that, but let me check that because the pH is fixed at 7.5, right? And let me see if that itself can give me the answer. So this specifies solid phases, right? And again I need to choose AlOH3, the amorphous form, right? And add that back to main menu and run MINTEQ. Okay, and now I'm going to look at species distribution. So Al3 plus, again I guess because the pH is similar to 8 the case earlier, it's going to be equal to 95% is present as AlOH4 minus complex, but how much of it is in the first case present in the dissolved form, right? So here you see that when you are adding AlOH thrice, right, and at pH 7.5, right, most of it is in the precipitated form, right, Al3 plus, most of it or almost 99.9 or 100% has precipitated out, and less than 0.1% is in the dissolved phase, right. So obviously what is the concentration of your particular precipitated solid? So that's more or less equal to what you plugged in earlier, which was 0.256 molar Al3 plus. So that's more or less equal to 0.256 molar Al3 plus, right. So I guess with that I can be done. Let me just look at what we have been up to. So I need to fix the pH and give the relevant components, and more importantly specify the relevant solid species, right. So list of possible species, we say that it was AlOH thrice amorphous, right. And why did we choose amorphous? I mean, if no one gives you the relevant information, let's say, you will assume that the least or the most soluble form of the solid which is formed first is the controlling solid, and in most cases it's the amorphous form, right. So with that I guess I'll end the class for today, and we are going to look at a few more examples or applications, right, hopefully real life examples, and then solve them by WMINTEQ and also see how to set up the equation by hand, right. So with that I am going to be done for today, and thank you.